Now we will move ahead with the demonstration part, the hands-on session. So I would request Paris to please continue the session.
Okay, ma'am. So first of all, thank you, Nikhil sir, for the wonderful presentation. Hopeful the students that have got a good idea about CAD and meshing. Before starting the session, I would just like to know everyone that today's session will be based on meshing. So have you used any utility in OpenFOAM called BlockMesh or SnappyHexMesh? Or if you are working on it for the first time, so accordingly I can settle my pace. So if you can just type it in the chat box that you are new to Snappy Xmesh, we can move accordingly. Okay, new to it, new. Okay, so the presentation is made considering the new students only. So uh, good afternoon everyone. My name is Paris Palkar and I'm working as a research assistant at FOSSEE CFD team at IIT Bombay. And today's session will be on detailed session on meshing using SnappyHexMesh. So before starting, I would like to thank the FOSSEE team for arranging such workshop, starting with Dr. Kanan. Dr. Kanan has just retired this year. He was leading this FOSSEE project and he was also a professor in the Department of Chemical Engineering at IIT Bombay. Dr. Chandan Bose sir. So Chandan sir is leading the CFT FOSSEE project and he is the PI right now. He is also a professor in the Department of Aerodynamics at University of Birmingham, and he is also serving as the visiting professor at IIT Bombay. And Payal ma'am is working as senior project manager in CFD FOSSEE team, and she is the reason we are having such wonderful workshops. So let us start the session. So what is meshing exactly? So before the let us consider a industry. If you want to produce an output or product, you have to check the product is well suited or not. For that, the industry goes through various lot of process. It can be structural or it can be related to fluid as well. So we are dealing with the fluid part. So we'll be only discussing about fluids. So let us say we want to find out how this is the position of the cyclist, and we want to find how aerodynamically it is suited for him to be in a particular position so that he can achieve uh, the maximum speed. So there are three CAD models that have been generated uh, with three different parameters and position, and the CFD study has been carried out for the same using any CFD software. So what is SnappyHexMesh basically? SnappyHexMesh is an open form utility that is used to generate high quality meshes for complicated geometry. Only the thing is this utility generates 3D meshes. So we have to create first a 3D mesh and then convert it into a 2D. There is a particular utility provided for that as well, and it is an iterative process where refinement can be carried out in particular regions of interest. So let's say I want to refine a particular patch meaning the STL or the domain of interest. I can do it using iterative process. We will see everything in short. And the mesh that is generated, it can be visualized or it can be accessed in the constant folder in the polymesh section of OpenFOAM. So, what is the workflow of SnappyHexMesh, or how can you start SnappyHexMesh? So, there are two ways you have to start meshing. First thing is block mesh or external mesher that will generate your background mesh. So, what do you mean by background mesh? We will discuss about it in some time. And the CAD model of which you want to conduct the CFD study. Once this background mesh is generated and the geometry STL file is created, it is not compulsory to have the STL file. You can have the object file as well, and there are various formats of the CAD file that you can import into Snappy. And once your background mesh along with the geometry it is generated, it is sent towards the SnappyHexMesh dict. SnappyHexMesh dict reads your background mesh and it tries to combine it with the geometry that you have created. And once SnappyHexMesh is executed, we get our OpenFOAM readable mesh that can be further used for your simulation. Okay, so what is the workflow or what is the idea of SnappyHexMesh? So the process generally starts with the creation of a background mesh. We generally use block mesh utility to make the mesh, and it is purely hexahedral and it defines the overall domain. And along with the creation of the geometry, like airfoil, bluff body, or any other geometry, let's say cylinder or flat plate, uh, the geometry is created. And once these two conditions are met, then we go to SnappyHexMesh, where the background mesh and the STL geometry are combined and is processed through the SnappyHexMesh dictionary. So before going to the CAD generation, the main interest is generating the background mesh. So there are three criteria that we need to define while generating the background mesh. If you are using block mesh, it is satisfied easily. But if you are using any external measure for this, so you have to satisfy these three conditions at least. So the first condition is the mesh must consist purely of hexahedral cells. So if you have seen the mesh in open form, the mesh should be particularly of it should consist of hexahedral elements, and the cell aspect ratio should be 1. Along with that, there must be only single cell edge intersection. So it is meaning that two cells should not intersect in between. The edge of one cell should be intersecting with only one cell of its consecutive neighbor. Okay. So now moving to the SnappyHexMesh dictionary. So there are three main parameters of defining your SnappyHexMesh dict. Okay. Firstly, we saw how the background mesh is created. Then we saw how the geometry is created. Now our domain of interest is SnappyHexMesh dictionary. We will be visualizing it, so don't worry. You have to specify these three parameters in SnappyHexMesh in detail. We will be seeing this in just a while. But this is castellated mesh control, snap controls, and add layers. So what this castellated mesh control does is you have to specify your geometry, your refinement region box, or is there any STL file or geometry file that is there, and how it will be read by SnappyHexMesh. So you have to define the name of the geometry as well. And in snapping, what it happens is when you have your background mesh and you have your STL, so the SnappyHexMesh tries to snap the body inside the background mesh so that we can use it for the further simulation. And if you are working on external aerodynamic cases or internal flow cases, you can also use this add layers section where you can add the boundary layers to your custom patch. And there is also a section of mesh quality controls, but it can be added into a newer dictionary and it can be specified. Also, we can just add a fourth column and we can define the mesh quality parameters as well. I have written some small commands here. This will be helpful once we start implementing our mesh. So just be with me for at least 5 to 10 minutes and then we will go to the actual demonstration. So yeah, as we know, the background mesh, again, it is base level mesh. It is just a basic level mesh, and it should cover entire of your domain. And this is the expected STL surface. It is an airfoil, and this background mesh is generated by block mesh dictionary. Then what we do is when we run SnappyHexMesh, the second procedure that occurs is the refining of the background mesh. So the cells of our interest are refined in the particular patch. It is done in castellated mesh controls, and the edges of this geometry are defined by the surface feature extract dict. We'll also see about it. So how are the refinement level done? So if you do not specify any refinement level, it will just consider one single cell. But if you particularly provide a level 1 refinement, so it will be dividing it into 4 sections. And likewise, if you divide the section with level 2 refinement, so it will divide the subdomain into 4 parts. And again, the domain will be segregated into 4 parts further. So as we go ahead, various refinements can be added and it can be implemented. And then the removing of cells. So as we know, we have a background mesh as a different entity and the STL as a different entity. So we want the STL and background mesh to be together. So we do the removing of cells, unwanted regions are removed, and this is done by specifying a point inside the block mesh dictionary with the utility called location in mesh. So you have to provide a particular point in your block mesh dictionary where we want our cells to be retained, and there are two ways to define it. If you define it outside, it will be considered as the internal flow, but if you define it inside the patch or the STL, it will be considered as for internal flow problems. And this is snap mesh to surface means then the snapping of your geometry is done using snap controls, and we will see about it in few minutes. And this is the final step of your mesh generation, and you can add the boundary layers to capture the accurate phenomena that is occurring in your particular case. Okay, before going to the tutorial section, I would like you to show how you can actually find any block mesh dictionary. Okay, so now as we know, if firstly you have to source your block mesh dictionary. So now we will be sourcing our homes dictionary, that is denoted by tilde. So we'll be sourcing it first. So we'll use the command source / dot bash rc. Then as I have two open form versions with me, as we have specified as well, it is always better to have two open form versions with you. So I have set an alias of open42412. It will notify me that your ESI version has been sourced and you are good to go working with the ESI version. If you want to source the foundation version, I have also created an alias. You can just write OF9 and hit enter. Okay. So here I can see the foundation version has been sourced, that is OpenFOAM 9. And if I want to source my ESI version, you can use the command that you have set in your bash rc of the home directory. And again, clear. And I'll go to my run directory. So run directory is the file location where your all the OpenFOAM 2412 files are executed. It is particularly denoted by your name or whatever you specify here, and you can run your OpenFOAM cases here. Okay, so I'll do ls. So if you don't know, ls command is used for listing out, and if I want to go in the FOSSEE folder, I'll do cd capital F, and if I hit this tab, it will directly capture what I'm trying to write. Okay, in the FOSSEE there are various folders, so I'll just quickly go in our topic of interest, and there are multiple folders. Okay, so if I want to find, I'll just write tutorials. So it is prompting key, there is no folders called tutorial. I'll just source my homes/rc again. Okay, so now I am in the OpenFOAM example session. In the installation session, we have answered where the tutorial folders are generally kept, and this command, there is this command called grep -r SnappyHexMesh in the foam example. I'll explain it. grep -r. So what this command will do is, this grep is generally used as search. So we are interested to search the SnappyHexMesh dict that is implemented in the foam examples. So when I'll hit enter, so it is listing out various files. If I do list out what are the tutorials that have been implemented, so if I list out, there are various solver, that is combustion solver, compressible solver, heat transfer, multi-phase, incompressible. So here you can see it will always locate key, let us say in the mesh folder. Do we have a mesh folder? Yes, we have a mesh folder, and in that mesh folder we have a utility called SnappyHexMesh in aerofoil NACA 0012. So you can just check out if you want to find any particular dictionary that is implemented. This is not just limited to SnappyHexMesh. You can also try to use, let's say you want to find key, is there any solver? Because what we do generally in OpenFOAM is we try to see the tutorial cases first, and then we try to set up our own case. So if you want to just find rather than just manually going in particular folder into folder, what you can do is just write simple foam. So you are interested to know where is simple foam in your foam examples dictionary. Okay. Again, it will list out which dictionary has used simple form. So you can directly go in. Let us say this CD is used to go in the particular folder. So let us say I want to go in mesh. I have hit a tab, so it has known what I want to write. Then I'll type snappy. It has again understood. Then I'll go in the motorbike case. Now I list out. So I have all these folders, and if I go in the constant, there are some files, tri-surface, turbulence properties, and transport models. I'll go in system. So if I tell us, so there is the SnappyHexMesh dictionary. We want to test how it works. So you can just copy this into the run folder where you want to run your OpenFOAM command. So now I am in my OpenFOAM terminal again. I'll go in FOSSEE and then see. So before that, so this foam clean tutorials command is used to clean all the case that was already existing here. So if I list out now, the case is clean and we can see one on one what is happening. So this is of a complicated geometries, means before starting any complicated geometry, it is always recommended that you should start from the basic geometry first, and then you can go towards complicated geometries. So now for this, we are using the flow over a cylinder case. We will be just meshing it. We will not be solving the case here, but we will just be meshing it. So this is the domain. These are the approximate dimensions. We will be manipulating it based on our need. And the diameter of this cylinder is considered to be 0.1. Okay. So when I go in the geometry making of this geometry can be easily replicated into FreeCAD, and then either if you want to export it in the form of object file, you can do that, or if you want to export it in the form of STL, you can do that as well. There are various commands or the various extension that the folder reads. And here, if you are able to see, I have used the diameter of this cylinder to be 0.1, but here I have specified it the 0.1 mm, and here I have specified the geometry as 0.1 meter. So like you might be thinking ki there is some discrepancy, but just to tell you ki OpenFOAM generally reads only the data that is related to that is in meters. So even if you make your geometry in meters, it will be read by OpenFOAM and PyReview in terms of meters only. It will not read it in mm. Okay. Again, there is surface transform points. We'll come to it later. So I will do list out. And again, so if you can see, this is the general case structure. If you want to visualize it on OpenFOAM, you can do that as well. If you have to just write tree, and it will list out what are the features are there. So this folder generally contains your boundary conditions. These are the all run and all clean files that will be executed if you want to run the whole case without knowing what is happening. This is the tri-surface folder. In try surface folder, we generally keep our STL that is being exported from any CAD modeling software. Let it be SolidWorks, let it be FreeCAD, or any other CAD modeling software that you are interested. You can just go to this try surface folder and you can paste your uh, STL of your interest. And there is this extended feature edge mesh tip. We will understand what is this. Then in the system folder, there are multiple files again: block mesh dictionary, control dictionary, decompose path, extrude mesh. And out of these dictionary, only few we are going to use today. So that is block mesh, uh, your SnappyHexMesh, surface feature extract, and at the end extrude mesh dict. As I told, SnappyHexMesh is just a 3D meshing software utility. We cannot use it to generate 2D meshes, so we have to just use an extrude mesh utility in the OpenFOAM. It is provided by OpenFOAM itself. So you have to just run this extrude mesh command, and you will be able to see the geometry that is created in 2D. Okay, so let us start. So firstly, if you can see all run, as we are running out of time, I won't spend much time on explaining all run file. We'll just try implementing the keys. So firstly, in any CFD simulation, the first step is the CAD generation, and the second step is meshing. So now we will be using block mesh. So it has created blocks, and there are four patches. Four patches are generated. They are namely outlet, fixed walls, front, back, and we can, if you want, you can also add top and bottom, inlet, etc. So you can add that as well. So if I want to visualize it, I'll make a folder with an extension .foam that will be readable for ParaView. So for creating that, I'll just write TOCL touch foam. I generally use foam. You can write anything. You can write CYL cylinder. You can write your own name as well. So I have written foam.foam. Now my foam.foam file is generated. I'll just navigate to it. Uh, I'll refresh it. So the foam.foam file is generated. I'll go in the ParaView and I'll try to visualize it how it looks. Okay. Okay, so we are in the ParaView. I'll open the folder here. So this is the solid color. If you want to visualize your mesh, what you can do is in the ribbon, go from surface to surface with edges. So it has created a finer mesh, and now I'll just reduce the opacity, and we will try to visualize how our STL geometry will look like. So now this geometry is very much transparent. Now we will try to implement, or we can try to see how the geometry is looking. As I told, we have to keep the folder in the try surface. So let us try to open this cylinder.stl. Let us open it. Okay, so as we are able to see, this is a 3D geometry. This is the 3D geometry, and it will look like this. But let's say you want to move it a little bit further. Just a minute, I'm on the axis grids. Okay, and this is the 2D view, 3D view. If I want to switch to the 2D view, what I can do is I'll hit the this ribbon, and now the view is 2D. So right now it is at -5, -15. And what if I want to go +5? So I want the geometry here. So there is again a command called surface feature transform. I have surface transform points. I've mentioned it here. So I'll go in the constant, and in constant I'll go to try surface, and I'll list out. So if you are new to any particular command, what you can do is surface transform points and -l. So it will list out what you want to do, means there are various commands that you can execute with this surface transform points with the options that are available here. There are multiple options that are available, and in the output you can give the surface file in as input, and you will get the output file again as the surface file. Okay, so now I have this cylinder.stl, and the cylinder.stl is at -15, so we'll just try to move it further. So what I'll do is I'll do surface transform points translate to, let us say, I wanted 5 points ahead, 5 meters ahead. So I'll give positive 5, 0, 0. As input, I'll give this file cylinder.stl. cyl is just the short form, cyl.stl. And as output, I want, let us say, you can define it on your own. Let us say cylinder3.stl. There is just a minor correction. Okay, so it read the surface from cylinder.stl and it has written it to the surface.stl, cylinder3.stl. It has translated it and it has ended. So we can visualize it in Paraview as well. 1 and 3. See, so the geometry has been translated to -10. So let us say if you make some change, some errors while making the geometry, you can rectify it using the commands that are inbuilt in OpenFOAM. Okay, so this part is covered. So we have now generated the background mesh, and we have also generated the cylinder as well. The cylinder is generated using FreeCAD. It is an open source CAD modeling software. You have to just specify the diameter in a XY plane. Just keep in mind that the XY plane here and the XY plane in the block mesh dictionary should be same, so that you can visualize your geometry likewise. Or if you made your geometry in YZ plane and you have made your block mesh in XY, so it will throw some error. So just be careful about it and you are good to go. You have to just extrude it in a particular direction, and you can work on it for your meshing. Okay, so this is the background mesh, how it looks, and this is the geometry of the cylinder. Then the certain commands to run. This is block mesh. We have seen block mesh. We'll be looking at surface feature extract. What surface feature extract is? This surface feature extract command is only for OpenFOAM 2412 or the ESI version. If anyone is using OpenFOAM 9 or Foundation version, they have to use only surface features. You can the command for command in OpenFOAM 9 is surface feature, and in OpenFOAM 2412 it is surface feature extract. Okay, so let us go now to the surface feature extract dict as well. You can use any of your notepad visualizer, but as I'm more comfortable in Visual Studio Code, I have installed it, so I'll just open it in VS Code. It looks good and you can edit it as well. So just change this to C++. Yes, so whenever you open any OpenFOAM file, this is the general thing that you will be watching. So in the foam file, this will tell you as the 2, and the format of this file is ASCII, and this is a class. This is a dictionary, and what is the object that is used in this dictionary is surface feature extract. Now let us go to the surface feature extract dictionary, exactly what it is. It is not a bigger dictionary, it is just around 20 to 25 keywords. So firstly, you have to define your STL, the same STL that you have inputted in your tri-surface dictionary, and you have to tell which extraction method that you want to use, that if you want to use it from surface or volume, etc., it can be used. You can also extract it from the edge as well, and the include angle. As we are running late, I have the visuals ready for this, but we are running late. If we get time in the evening slot, as I'll be only presenting the session, I'll demonstrate what is the significance of this include angle. Then the subset features, that do we want more than one or two phase connected in this. So when Nikhil sir said in his previous session that you can use CST multi-region form for heat transfer related studies. So whenever we make multi-region meshes, we use this command to true and open edges, that as we want our edge to be kept as one with the consecutive neighbors, we have written it as yes. And write object, so it writes the object as emesh in the try surface folder itself. So I'll just run the command now. I'll open the terminal. Okay, so I'll write. Now I'll just write surface feature, and this has given me feature, and now I want to extract. Okay, so it has written this particular file, the STL file, into an image file. Why this image file is important, we will see in the SnappyHexMesh utility. The execution time was 0.1 seconds, and the clock time was 0 seconds, and it has ended. It has written everything. If you write 3 here, so here you can see this cylinder.emesh is generated. You can also generate the emeshes for this cylinder 2 and cylinder 3. The only change is you have to specify the this name in your surface feature extract dictionary. So this will be changed to cylinder 2. Okay. So this will be the name, and you can generate the image for this particular folder also. Just keep in mind, name the file that you are intending to make the meshes of. Okay. Okay. So now let us go to our SnappyHexMesh utility and understand everything in detail. You can just drag it and keep it here. Yeah. Okay, so this is the SnappyHexMesh dictionary. Again, it is written, the format is ASCII, the format in which it is written, and it is again a dictionary, and it is an object that is written in the dictionary. So whenever we type the SnappyHexMesh command, our terminal will catch it and try to execute this dictionary. Okay. So as I said in my presentation, there are 3 fields that you have to enable: castellated mesh, snap controls, and add layers. So these are set to be true. You can always use false to turn to switch off the any particular domain if you are not interested to use it as of now. So what we can do is we can use false for add layers, and we can save it as of now. So we are not generating any layers right now. We will be generating as we move forward in the tutorial. So then comes the geometry section. Again, you have to define your geometry, the geometry that you are using, and the same geometry that has been used in the try surface. Again, it describes all the input geometry required by SnappyHexMesh, and this is the file name of the geometry that has been placed in your try surface. And we are asking it to read it from the type is try surface mesh, and we are asking it to be named as CYL cylinder. You have to specify it here, because we will be using this patch as CYL only further as well. So in the geometry section, we can add we can add multiple refinement box, but as of now we are just using 2 refinement box. You have to just specify the minimum and maximum coordinate for your refinement box, and once you execute SnappyHexMesh, it will start to add the refinement box in your particular region. Okay, again we have added second refinement box. So generally refinement is given in aerodynamic cases to capture the wakes that are occurring in the external aerodynamics cases, so that we can capture and model it very accurately. Okay. So now let us go to the castellated mesh controls. This is the first part of your SnappyHexMesh. So it controls the refinement parameter. So there are some entries that I will explain you. So this is maximum local cells. So the 10,000, it represents the total number of cells your single processor will use, and these are maximum global cells. So this is the total number of cells that are allowed in your total simulation, you can say. Then minimum number of refinement cells that are used, 10 here, that are required per iteration. If you want to refine 10 cells, at least they are required. If we do not satisfy this criteria, the SnappyHexMesh will crash. And this is max load unbalance. So let's say if you have local cells and it is exceeding the amount of 10,000 cells per processor, what will it max load unbalance will do is it will try to segregate it to other processors, so the 10% usage is divided to another processor as well. This generally comes in place when we are running in parallel. We will be looking for serial and parallel as well. And if we want any buffer layers between different levels, so yes, we want. So the entry is n cells between levels, and we have kept it as 10. Okay. So now in the castellated mesh, there are features. Features in the sense file means what features that we want. So the file name is cylinder.emesh. It will read the image from surface feature extract that we have generated, and we want the refinement level of 2 for our image. Okay. And then we will go to surface based refinement. So it will refine the cylinder that we have, and for cylinder patch, this is the same name that we have given it in the geometry section as well. So this is user specified name, and again this is user specified name. Okay. And now we want the level to be 5. Again, here there is a catch. If you are using OpenFOAM version 2412, you have to specify it in the terms of close brackets. But if you are using OpenFOAM 9, you can just simply prompt a single number and the mesh will be done. Okay. So now resolve feature angle. So if there is any edge refinement, so if you want to capture it or not, based on this the feature angle is given. Then refinement region. Refinement region is particularly given to a particular region. So there are two regions. First is refinement box 1 and second is refinement box 2. So there will be a second level refinement, as we can see in the presentation. The blocks will be divided. Every block in the particular refinement region will be divided in 2 levels at least, as we have fixed it. We can change it as per our need. Again, refinement box 2, this is also same as 2, and where we want it as inside, there are three parameters that you can specify: inside, outside, and there is one more parameter as well. And location in mesh, this is you can star mark it. It is very important parameter. If you misinterpret this particular filter or this particular line, your whole SnappyHexMesh will crash. Okay. And if you can see, wait, let me show you my, okay. So I'll visualize it afterwards. Just for right now, I'll just explain what is the block dictionary. And if we want freestanding zones, so means if there are any bound or there are any domains that are not part of our geometry, this freestanding zones, it considers them as well. So now we'll go to the snap controls. This is the second part of the SnappyHexMesh dictionary. So there are various entries. So first is smooth patch. So if we want smoothing iterations on our patch, so what level of smoothing iterations we want on our patch, so it is defined as 6. And while snapping, what should be the tolerance between two cells? how close the points are required to be snapped when we are converting the STL. That means when we are merging our geometry background mesh to the cylinder, what should be the tolerance of the 2 points that we are trying to snap. Okay, then this is n solvator. So it decides the mesh displacement relaxation, and these are relaxation parameters for meshing. And if we want edge based snapping, let us say you are working on an airfoil or something, or as we are working on the cylinder case, we have an edge, so we will give this feature 15 for the n feature snapper, and implicit feature snap and explicit feature snap. So this is something that I mean you can, if you turn on implicit feature snap, SnappyHexMesh will try to read the geometry on its own. But if you turn on the explicit feature snap, we have to define it in the upper region that we have mentioned, cylinder. This is user specified geometry. So if you want to specify the geometry in your SnappyHexMesh, you can specify it using explicit features. But if you want to SnappyHexMesh to capture it on its own, you can just turn on the implicit features as true and then add layers. So as of now we have turned the features of add layers as false. We will be not, the whole add layers features will not come into the place, so this will not be useful. So let us go to the terminal, and now we can write snappy hexmesh. This override commands, what it does is it will help you. Okay. So what override command does is it will override any existing, if you have run any SnappyHexMesh feature previously. So if there was any mesh earlier, it will be overwritten by this command that we are using. This should be done within some time. Let us wait. Okay, so this mesh is generated in 22 seconds, but the paraview is looking very clumsy. So what I'll do is I'll just turn on this as well, layer control as well, and we will run the SnappyHexMesh again. So there was one SnappyHexMesh that was used without adding the add layers feature, and now we are again using the SnappyHexMesh feature with layers. So I'll again just write SnappyHexMesh override. It will erase the existing mesh and write the one again. So it should be done within some time, 20 to 40 seconds max. Let us wait. Okay, so the mesh is generated in 20 seconds, and I'll now just zoom out a bit. So what I'll do now, I'll just go in the folder section and I'll open the foam.foam file that I have, and I'll hit apply. So now the geometry is done. We can also see it. So the snapping is done quite well. If the snapping is not done appropriately, there will be some cracks that you will be seeing here. But our snapping is done very good. So you are not, means there are no visible sign of mesh cutting. So I have just switched to the 2D view for better visual purpose, and I'll just now showcase surface with edges. So now there is one refinement region that has been added, and inside it we can zoom more further. I hope you are able to see the boundary layers that are occurring. So we have specified the number of boundary layers to be the boundary layers are expected to be 4 with the minimum thickness of 0.01. How this has come, I'll also discuss about it. So I mean, the due to my limited RAM as well, I'm not able to go much further. But if you are able to see, you can see the boundary layers are being generated in this region, and the further refinement is also done in your total domain. Okay, so your mesh is generated, but you are not sure about it, ki, is it good enough or not. So what you can do is, you can go in your terminal and just use the command check mesh. So this check mesh command is used for checking is your mesh good enough or not. So it is checking and it has prompted me the mesh is okay, you can work with it further as well. Also it will list out what are the patches that it is using. We have specified them in SnappyHexMesh dictionary, and the details of the patches as well. Okay, but the thing is, you won't be able to visualize it in paraview. Let's say you want to visualize it as well. So what you can do is, there is a command check mesh hyphen help. So it lists out what are the existing commands that you can use. So for this, we are using write all fields. What this command will do is write the fields with mesh quality parameters. Okay. So what I will do is check mesh write fields. It is writing. Okay, it has ended. Now I'll go and just refresh my file. It is happening. Okay, and now let me just skip the zero time. Okay, so now you will be able to see various parameters that we have given in the mesh dictionary. You can read about it as well. If you want to, let us say you want to check the aspect ratio, and so here the aspect ratio is near 1 to 2. You can zoom it a bit to see if there are any if their aspect ratio is increasing or not. So I don't think the aspect ratio is increasing as of now. There are some other parameters as well. What is the skewness of this mesh? So it is basically some skewed, but it is not in the domain of our interest. The cylinder, it is very much pretty much okay. You will be seeing some skewness due to the boundary layers that are generated, but you don't have to worry about that. Okay, and you can also visualize orthogonal angle or thickness of the particular cell. You can list out every parameter that you are interested in. Okay, so this is our mesh. This mesh utility is being used using serial processing. What if I want to run the mesh in parallel? So again, you have to do nothing. Just go in, and here it is cylinder mesh dot parallel. There is only a change of command. I'll show you. So all run parallel. What it will do is it will run all of your domain in parallel. Wait, let us do it. Let us wait. It will take some time. Okay, it is running on oral run. I want to run it in parallel. So it has called MPI. It is used for running parallel simulation, and we'll just wait till the parallel meshing is carried. So it is reconstructing. Okay, so extrude mesh is done. So if you can list out, it has decomposed your domain into 4 processor 0, 1, 2, and 3. So we can see what is happening here. we need to also make a foam file to visualize our mesh. We have created the foam file. Just copy it and paste it in every processor that you have. There are 4 processors, so we are just pasting our foam file in the 4 processors to view which processor is handling which mesh. Okay. So now I'll go in file again, and rather than working in this case, I'll go to the parallel mesh, and in the processor there is 0 processor. I'll open this file, apply, and it is coming out to be some weird, so I'll just give it surface with edges and color it with red. Okay. And double clicking, I'll just change the name of it as 0 processor. Okay. Now I'll open another second processor, 1, and I'll hit apply. Okay, so it has constructed something. Before going there, we'll just change the name to processor 1 underscore. So we will open the third and fourth processor as well. So now it has showed something. We'll again write it as third underscore processor, and we'll now open the fourth processor. Okay, and apply. Okay, so it has captured all the domain underscore 4 underscore 4. Okay, so what we can do is, this is the 0th processor, this is your first processor. I'll change it to surface with edges, and I'll just color it. Let us say yellow. So this is your yellow domain. This is your third processor. I'll color it with green, so it is using green. And this is the fourth processor. Let us pink it with color it with pink. Okay, and change it to surface with edges. So here you can see there, in the previous case when we were running it on the serial, the single processor was tackling the whole domain. But once we have decomposed it, now 4 processors are taking care of it. So we can see the regions as well. Okay, and if you want to load the foam.foam file, you can load it, hit apply, and just as we have reconstructed it, here you can see reconstruct par, so there will be an issue. But if you are not using reconstruct par, you have to just write decomposed list. Okay, so we can see our mesh. So I'm just winding up due to time limitation. Just a minute. And the last utility that I want to explain you guys is the extrude mesh utility. I'll open it. So it is again very small utility. This utility converts your 3D mesh to 2D mesh, and the name of the input STL that we are using, that is cylinder, and we want it to extract from the surface that is present, and this is surface feature extract. Just a minute. Yes. Okay. I'll try zooming it. I hope the code must be visible. Okay, so this is the extrude mesh utility, and you can basically convert your 3D SnappyHexMesh to 2D SnappyHexMesh using this utility. So we want to construct it from patch and source case. If you have a particular, let us say you want to extract it from this particular address, you can use this. But as we are in the same directory called cyl mesh, and we want to extrude this mesh only, so we are not using any address. You can just give a dot and it will work. and source patches is the which patch do you want to extrude. So it will be the front patch, and what patch will be it exposed till the extent it will be exposed. So it should be back. And how we want it, so we want it linear normally. Let us say so this is our domain, and I want it to be extruded in the 0.07 meters in the linear direction. So I can specify this in this particular section. If I turn negative, it will be just it will be extracted in the frontwards. As I have given positive, it will be extracted backwards. And flip normals, if you want to flip the means it is just basically opposite of where you want to locate your mesh, means visualize it. If you flip it, the extrusion will be done frontwards. If you keep it false, the earlier commands will be taken place. um, that's all from my end. Actually, I had some things to show, but as we are running out of time, I feel like we should stop. Anyways, in the second session, I am going to present the heat transfer case study, so we can discuss more about meshing as well as heat transfer in the Q&A session. I have prepared some post-processing visuals for you guys as well, so we can have a discussion on it also. Also, if you have any questions, you can post them in the chat box. Uh, is it okay, Payal?
Yes, absolutely fine. So, whatever questions you have for Paris now, you can just note it down somewhere. And after Harish's session and the next demo session, we can take it up. Thanks a lot, Paris, for the presentation.
Thank you, ma'am. Thank you,
Yeah.
everyone.